All right. As John was previewing, this is going to be a discussion of how all the numbers come together for the performance budgeting. So I'm going to start in the context of the requirements, which is to say, CGI is a tech demo and we're funded to do things at a level that proves that the concepts work. And then I'm going to drift a little in the end towards where could we go from here, but in sort of a hand-wavy, approximate way. So at the top level performance, the way that the question to CGI is structured is to specify one particular observation, one particular context for an observation. So we have a fifth magnitude target. We have, everyone should recognize that that is a very bright planet, a flux ratio of 10 to the minus 7. And that colors a huge amount of the contextual questions that I'm going to try to address. We're in what we call band 1, visible wavelengths. The requirements only speak to 6 to 9 lambda over D. Another important part that just colors the details of what we describe is that there's a pre-specified 10-hour observation. And that's this is basically setting a whole bunch of independent variables and then just leaving you to identify the noise, which I'll get to in a second. So it's the star has a specified size. So in real terms, the bottom line that matters is we are told, if we were given a hypothetical 10 to the minus 7 flux ratio planet, the job of the instrument is to make a measurement that is sensitive enough to give an SNR of 5 photometric measurement on that 10 to the minus 7 planet. So those two numbers taken together, 10 to the minus 7 flux ratio, sigma minus 5, says that the noise in the measurement that the instrument delivers, we can't deliver the planet, but we can deliver the measurement. The noise in the measurement that we deliver has, the noise is 2 times 10 to the minus 8. That gives an SNR of 5 on the planet that was provided to us in this hypothetical context. So the instrument job is to maintain a cap on measurement noise, not to provide the planet. So that's all nicely quantified and specified. I will talk a little bit about requirements, the detailed language of the requirements. As an instrument, there's a mission and an observatory that are responsible for actually delivering all of this in the end. That includes things like the telescope has to do what the telescope needs to do for us to make this measurement. And, the ground systems have to operate, all that. So the mission and the observatory are responsible for all this. At the instrument level, we come in at what's called a level 3 requirement. So that's the context I'll speak to in the beginning, and then I'll diverge a little bit from that. So John did a hugely better job than I possibly will with the context for differential imaging. This is just, a graphical recap to say that when we talk about the flux ratio noise, when we talk about the ability to do a good measurement, it's in this context after the differential measurement. It's in the difference between the data we took on a target star and the data we took on the reference star. It's in this context, post-differencing, that we're quoting noise. So, the speckles themselves, the contrast itself has been subtracted to the level that they remained stable. So contrast stability how much did the speckles, which dominate your impression of what's going on in the two dark holes, if they're stable, they don't appear themselves in the RDI image. There is shot noise that's a product of how much starlight there was there and the time you spent observing it. But I just want to keep that context really clear. It's the post-differential field that is the context for noise that we describe as flux ratio noise. So the 10-hour part, John already showed, a better graphic, I'll say, for what we're talking about here. After we finish doing HOFs and getting the dark hole that we wanted, we spend a little bit of time sitting still on the reference. We visit the target, in this particular case, 4 different times, and then we go back to the reference. So I will say, as a preview to what else can we do outside of the context that we were given as a level 3 requirement, we can keep, this becomes a modular, cyclical option. We can just keep doing 10-hour measurement after 10-hour measurement as long as we want. The earlier OSs, we would go on for hundreds of hours. And there's sort of a simple extension of this 10-hour observation to however long of an observation you want. So OS 11 in particular, we did a few cycles. For level 3 requirements, I'm only going to talk about 10 hours, but recognize that the same concept is easily extended to arbitrary lengths. And we do have in the official OS 11 context, every 24 hours we do one iteration of HOFs just to keep up with drifts, just to keep the contrast from getting progressively worse as the long observation continues. That doesn't play into the 10-hour requirements context, but it is present for this extension to longer and longer observations. The instrument is not responsible for the wavefront stability coming into the instrument. So there's a bit of a, as John was talking about the low performance, there's a guaranteed level of stability that's baked into the specification that CGI receives from the rest of the observatory, but the margins are huge. It's, John was showing tens of picometers peak to valley, and the numbers that really matter are much more the hours-long averages of those numbers, which are even better than those peak to valley, tens of picometers. So just to say, another one of the challenges in describing this context is to distinguish between the guaranteed levels of wavefront stability and the modeled levels of wavefront stability. I'm a teeny bit guilty here. This is actually, I reused a graphic that was OS 10. OS 11 is, I can't remember how much better. It's a bit better than these. The story remains the same, that I just need to be clear when I'm talking about guaranteed levels of stability versus predicted levels of stability. And these do already include model uncertainty factors. So just to continue that same statement, one more step, the idea that we have a context where the stability is guaranteed not to be worse than a certain amount. That's a relatively loose specification. And so we have to demonstrate that CGI will produce good enough results even under the worst scenario. But we can use the exact same machinery to say, well, separate from the letter of the law that we have to do that well, we can just turn the crank on the same numbers for what the observatory modeling expects that stability to be. So for this talk, since this is not a, does headquarters accept that we are sufficiently mature to launch, I'll talk to the what we call the mission CVE. This is where the stability is as predicted, not the stability is only as good as guaranteed. So that's the context that I'll be continuing to talk about. But in this budget, which I'll dive into more detail in the next slide, this still has this context of a 10-hour observation on a very bright planet, a 10 to the minus 7 flux ratio planet. So I'm going to stick to this constrained starting point, which is the same as what our requirements are written in for the time being. And I'll talk about how we do under that, a tech demo level of performance in the structure of the budget for the moment. Just to say, most of the numbers that you see here are in units of parts per billion. They're in units of 10 to the minus 9. So a 10 to the minus 7 flux ratio is 100 times 10 to the minus 9. But this just turns all of our numbers for comparison purposes into, hopefully mostly single-digit numbers, single-digit parts per billion. So just to describe, this is a budget, and so there are lots of contributors, and you can think of it as a flow down of requirements. You can think of it as a roll up, where you take all the individual contributors and add them up to see what that gives you. So the level 3 FRN requirement, as we said, is to give a signal noise of 5 on a 10 to the minus 7 planet. I'll zoom in a bit. This is small stuff. So a signal noise of 5 on a 10 to the minus 7 planet gives us our 20 parts per billion, 2 times 10 to the minus 8 flux noise requirement, flux ratio noise requirement. And then it gets broken into 3 branches. Without looking at the numbers, I'll describe the 3 branches. One is calibration errors. This is basically the conversion from I got 50 electrons to, oh, that means that the flux ratio of the planet itself is, 2 times 10 to the minus 8. Apologize that the same numbers as always, but so the calibration errors are how to put signal into the context of flux ratio, and these scale with the flux ratio. So the way to think of this is, if I just look at the CVE number here, which is 3 times 10 to the minus 9, compared to 100, the 10 to the minus 7 planet, these errors, for the most part, are always going to be 3% of the planet flux ratio. So this is saying, oh, I have a max SNR of 30 because I didn't calibrate any better than I needed to for a max SNR of 30. That's a pretty good SNR. So the fact that we're beating our SNR of 5 requirement is sufficient to say, hey, we didn't pound on this number and come up with more complicated calibration schemes, even though if you look ahead, this is the biggest number of the 3 CVEs that I'm about to sum together. This is high because this planet flux ratio is bright. So that's the calibration branch. The photometry branch is what most people are used to thinking about for astrophysical measurements. So you have a combination of shot noise from the star. That's to say that the contrast is a measure of starlight, and the starlight has shot noise. There's a contribution from the planet itself. Again, because this is a bright planet, a 10 to the minus 7 planet, because it's a bright planet, there's actually a lot of shot noise in a 10-hour observation. This is, almost sufficient for, let's say, an SNR of 80, if you were just looking at the shot noise of the planet by itself. Then there's exozodi, and there's zodi and exozodi. There's accounting for the fact that we spend time on the reference star that is pure noise without any target. There's detector noise. This is the standard, read noise is a bad example with a high gain EMCCD, but there is clock-induced charge and dark current that have noise associated with them. So these are pretty typical, I'm making an astrophysical measurement and I have these sources of noise from both the detector and shot noise. These will scale with exposure time. If I were to spend more than 10 hours, I would get more than an SNR of, whatever this number turns out to be, 50 some odd. So if I wanted, to decrease this number for a 10 to the minus 7 flux ratio planet, I just expose longer. I increase that integration time beyond 10 hours. This branch is stability. This is very specific to our differential context. The statement that I made that, all of our flux ratio noise is measured after we do the differencing of target and reference. The math of that is all contained here. Like I said in passing, if the speckles, which are starlight, if the speckles were to remain the same and you difference them, you would get a shot noise component. You didn't measure the speckle brightness with perfect accuracy. But if the speckle brightness itself were the same, this would be stable. There'd be no contribution in this stability branch of the budget. So this is entirely an accounting of how much did the starlight change? How much did the speckle brightness, not in a mean sense, not like when we quote the mean contrast in an area, but for the measurement of one planet for one photometric aperture, basically, think of it as 1 lambda over d, in just one speckle location, how much did that one speckle maintain its brightness such that when I take a difference, that one speckle subtracted itself off. So this is the speckle by speckle. How much did the intensity of that one speckle change between what I measured on target and what I measured on reference? So this is the sort of well, I won't say it's exclusive to coronagraphs, but I will say it's exclusive to the differential context that we choose to do all of our reporting in. John mentioned post-processing factor. This is at the instrument level. This was not considered the responsibility of the instrument in its delivery. We did, make sure to justify the magnitude in an approximate sense. And that's the study that John pointed to that showed, improvements of about this level after the differential classical subtraction was finished. So in this budget, we have just a taxonomy of different types of contributions to this instability. We roll it all up and we say, this is how much the speckle brightness changed during the differencing. And then we apply a post-processing gain as, people analyzing the differential data will be able to get an even bigger reduction by this value. We're not trying to get this number right. We just use it as specified. And the real answers, will be as accurate or not, depending on what this number turns into. Okay, so that's the layout of this budget. These 3 branches: calibration, photometry, and stability. From TVAC, that's the title of this talk is about TVAC results. And so from TVAC, we did measure. We got estimates of some of the calibration activities by doing those calibration activities in TVAC. We do have updated numbers on the detector, on the contributions from the detector by itself. That's things like clock-induced charge and dark current rates. I'll note that we don't have any update on shot noise contributions because those are astrophysical. Those are set by the brightness of the planet. I misspoke slightly. This number was updated based on the contrast level that we did see in TVAC that does determine the shot noise due to that starlight. But the planet shot noise is pre-specified. There's basically, not a lot that changes that. The stability numbers all got updated in various ways. The biggest factor for the stability update is by knowing what the initial contrast was. The contrast when we stop DFC is the contrast that you start observing with. And specifically the breakdown between coherent and incoherent, if you remember, Eric talked about it yesterday, Han Ying talked about it this morning, John mentioned it as well. That's a really important distinction for the stability calculations. The larger your coherent contrast is, the greater sum of these stability inputs, the disturbances, the greater impact some of these disturbances have for higher coherent contrast. And so these have been updated, all of them have been updated to include that. We also had some very easy to read off of the data inputs, like how stable was the DM temperature. Caleb yesterday showed the sensitivity of the DMs to changing temperature. As he said, that's the flip side to how stable is the temperature. So we had that input, and it's fantastic. This turns into a complete non-issue given the thermal stability we did achieve on the DMs. So, I can go through individual numbers, but the real answer is there weren't any surprises. Given all of the things that we measured in TVAC, our estimate of this 10-hour observation on a very bright planet is very nearly what we've been reporting for years. So the microphones in the room aren't sensitive enough to catch all the cheers and the gasps of excitement, but they did, good. So the margin we have against our level 3 requirement is essentially exactly what we've, within a fraction of a percent, is about the same as we've been quoting for quite some time. So that's good for this context, for this 10 to the minus 7 planet and a 10-hour observation between 6 and 9 lambda over D. So I'm not going to.
Just a quick time to let you know you're at 22 minutes.
Okay, thank you. So one context for all of this reporting is a bit of a bait and switch on the term, current best estimate. So CVE is supposed to be a current best estimate, but it isn't. For most of the engineering work that we do in requirements flow down, it's not a best. We're reporting. Let me be specific. Many of these stability terms are conservative in the way that they're calculated. And so when we plug the inputs in, the temporal statistics, for example, still remain somewhat of a worst case scenario. So for a lot of these inputs, this is not a true estimate. This is an upper limit. It's saying, it will not be worse than this. And so when we're quoting, a best estimate, we're quoting the margin or the roll up of everything altogether into a flux ratio noise. This is not how well we will actually do. This is what we can say we won't be worse than. So there's a little bit of engineering conservatism just in the structure of the numbers that we do. And I've said this a dozen times. This is all very specific to this. What does it take to be a tech demo that checks the box that we demonstrated the technology works? And that's this very bright 10 to the minus 7 flux ratio planet and a 10-hour observation. So I just want to kind of touch on how these numbers scale and a very hand-wavy thought process as to the numbers that people really want. How will it really do? So I've already mentioned that this whole calibration branch is really fractional to the flux ratio of the planet. This CVE of 3.33, conveniently enough, is an SNR of 30 on this flux ratio of a planet. That ratio basically stays the same. So if I choose a fainter planet, I'm still limited to an SNR of 30. I should be so lucky, based on the calibration errors. I should also point out, this is not This is unrelated to the statistics of false positives and false negatives, for example. This is the difference between, oh, I said it's a 2 times 10 to the minus 9 planet, but it's really a 2.05 times 10 to the minus 9. This is not a false positive, false negative. This is just a scalar error. The photometry noise, you do better on this by longer integration times. So if we, instead of 10 hours, went 100 hours, that's great. All these numbers drop. So let me be very careful. The biggest term here in this branch, if I look at all the CVE numbers, zoom in a bit so that you can see the CVE numbers. If I look at all these CVE numbers, the largest of the CVE numbers is the planet shot noise because it was a bright planet. So if I ask for a fainter planet, this can easily become smaller than the starlight shot noise. In both cases, not only will I do better on the starlight shot noise with longer exposures, but all of these numbers. So if I want to decrease this number and get a good measurement on a fainter planet, part of that comes for free because the planet is fainter. Part of that comes for the contrastability. Oh, this is a warning. These two numbers are mean numbers. This is the total starlight. These numbers are all standard deviations. This is all how much starlight, how much residual starlight was I over or under subtracted by, plus or minus this amount after I difference things. So don't be confused that these are large numbers. These are mean. These are standard deviations. And it's only the standard deviations that I compare to talk about noise. So the real wild card here is how much better can I do on a fainter planet if I want to do a 3 times 10 to the minus 9 planet with an SNR of 5? How do I get there? As I said, the calibration takes care of itself. I expose longer to get my photometry noise down. How do I get my stability noise down? And there are two things, there's sort of 2 or 3 things to say about the largest contributor to the stability. And those are that the first question is, how much better can I make my initial contrast? Eric spoke to this in his talk yesterday. We had a predefined period of time to do EFC and TVAC, and we posted to a resolution of that time period where we weren't scrambling for the extra last little bit for that last second. We were just trying to stabilize a well-measured number given that time period. If we were to get another factor of 2 in coherent contrast, in principle, we shouldn't be able to do much of our incoherent contrast. There's a bit of a mystery there. If we do better by a factor of 2 in our coherent contrast, that's a lever arm to make these numbers drop to the point where you could make a reasonable SNR of 5 measurement on a 3 times 10 planet. So that's encouraging. Ying showed model results, trying to match the TVAC results. There's, a continuation of that effort to ask, what if we, apply the aggressiveness we can with our regularization and the time that it takes, not in the observing time that I was speaking to for reducing shot noise, but in the EFC time. If we spend another 200 hours on EFC, can we get another factor of 2? Is it worth it? Yes. Would we do it, and would it produce the factor of 2 in coherent contrast that would let us see these faint planets? There's a modeling question there. And once we're on orbit and we get some real world answers about our contrast in orbit, that's going to be a hot. So, all I have are sort of hand waving. You can plug in any number you want and get any answer. But the short answer is, if we want to start to look at scientifically interesting flux ratios, it's not out of reach but it's, it's going to require more concrete information than we have today. If you want to get down to 1 times 10 to the minus 9, you're going to need to really work on post-processing. You're going to need to rely, more heavily, perhaps on tailored observations that specifically tickle some of these, most problematic stability concerns, so that you can identify them and make a library of what aren't planets in order to leave you with a better understanding of what aren't planets. That's not part, for example, Marie Ego's studies, are not about how would you build the best library you can to do the best job. They were in this constrained context of basically a single measurement, this 10-hour observation kind of thing. How well do you do there? So we can do better, with some, creativity coupled with, modeling and some validation. So very touchy-feely, very hand-wavy, but, modest flux ratios are probably within reach, and more aggressive flux ratios are going to require, something we don't have in our and that's, I'll just stop there.
Also, I have
Now maybe one.
Yeah, okay, let's see. The one question, yeah, Chris.
Yeah, so maybe this is a programmatic question. I was just looking at the agenda, but are we going to hear about the commissioning plans to achieve that calibration precision on Sky? Because presumably you've achieved it in the lab, and that's where these CBE numbers come from, but it's different on Sky, obviously.
I don't think we're gonna go into a lot of detail on the commission.
Not that much detail
Yeah,
for now, yes.
Okay.
Right, yeah. And Aki had a question earlier.
Oh, possible, I got it answered, actually, never mind.
I have one. Brian, if you go back to part 3, the internal contrast stability that you were showing in the error budget. So that number, you listed that it was dominated by Lofus effects. Does that also include things we learned about the DM drift during TVAC? Or is that?
Yeah. Yeah, so the DM drifts are a funny operational side note. So we still win. So there are 2 primary DM drift categories. One is the PMN effects, or, well, we're still not sure it's all entirely PMN. It could also be the DM structure. So there's there's temperature stability and temperature related drifts. And then there's these very long-term, weeks-long responses to voltage changes. And the responses to voltage changes, we just win by not changing the voltage. We in an HLC-centric mission, we say, we start with the seed that we got in TVAC. We do some touch up in orbit commissioning, the very first 90 days of the mission. We do some maybe large scale touch ups because we have to flatten the telescope and include the real wavefront error. But otherwise, by the time, 18 months is up, we've just been doing HLC. And so those DM voltage related drifts become very thermal drifts. The good news from TVAC is that the DM temperatures are sub-millikelvin in the temporal statistic that we care about. The average temperature on target versus the average temperature on the reference star. The DM temperatures fantastically. So just to answer half of your question, we didn't learn anything about the voltage change stability from TVAC. We learned a lot from the DM level testing. 2 years prior. The temperature stability we learned is just as reassuring as we wanted. So what I did say, I'm trying to remember which, it was, I did say here, well, wherever I said it, the dominant terms in the optimistic context are LOFS-related issues. I will disagree with what John said about tailoring the control bandwidths of LOFS in the optimistic case. There's a different stability context that says that the noise that you saw in John's plot, where LOFS was doing, acting on its own noise rather than any inputs and producing large residuals, there's a sensitivity to that RMS error. There's a far higher sensitivity to the, systematic's not quite the right word, but the mean level of residuals on target versus the mean level of residuals on reference. And that statistic isn't at all, like you can't see it at all in the plots that John showed. But those numbers are actually not too far off of what we want. So there has, if you take a top level context of its FRN, you tolerate a lot of the noise induced back and forth in exchange for the part you're more sensitive to. It's kind of, the story is worse than you thought. The story is worse for the mean being different on target versus the mean on reference. And so when you ask that question directly, you end up being kind of okay with the LOFS parameters we have. The main problem we have is that the camera, the pixel by pixel 0 point, the bias pattern, if you will, on low cam changes over time. And that gets projected into most modes. It gets projected into tip-tilt, it gets projected into stigmatism. And so you start correcting things that are based purely on camera length. And that's currently baseline to be our biggest optimistic problem. If we get past all these other issues, that's, so I didn't say enough about it in the slides to make you understand that without me saying it. But as we go down that route, that's the actual problem that we have to deal with when we reach that